Hi everyone and welcome back to your channel FE Civil Exam with Farhad, Mechanics of Materials. In this example, we want to calculate the maximum deflection delta max for a non-prismatic beam. So beams generally categorize into two main categories, prismatic beam and non-prismatic beam. So the first category, prismatic one, are the beam with the uniform cross sections, and the non-prismatic are considered like beams with a, a, a non-uniform or un, non-uniform cross sections. It can be an abrupt change or sudden change for example, the combination of different sections or a continuous change in the cross section. As you can see, both of them are an example for non-uniform cross sections, which leads to a non-prismatic beam condition. So we want to calculate a two simple supported beam with this height of h naught at its center and a concentrated load of P. We already calculated we already know what is the deflection if the beam cross section was almost uniform. Like you can consider a rectangle for that. So for such beam is easy to calculate delta maximum due to a concentrated loading. So if you remember that, or if you look at the references, that's PL cubed over 48 EI, considering the length of the beam is equal to L. But this time we want to solve it for a non-prismatic scenario. So let's see how can we approach this condition. So the length of the beam again is L. We are looking for the maximum deflection or delta max at the center for this non-prismatic beam with a concentrated load and two simple support beam. Let's approach our problem. From To solve the problem due to the symmetry for half of the beam, we can use a rolling support at the center and apply half of the load, that's like P over 2, and solve the problem or delta maximum for half of the beam, and due to the symmetry that's the same for the other half. So if you remember from one of our previous examples, which I provide you with the link on the description of this video, for cantilever, a non-prismatic beam with concentrated load of P, we already calculated the delta maximum for such beam is equal to 2/3 of PL cubed over 3 EI. So now back to our problem. If we have this condition, half of our original beam, and we can just bring this support to the rolling support, and it just fix the location, because in rolling support we have like the up and down movement. If we just bring this support there, it just prevent from that, so it just convert it to a cantilever or a fixed support, and then also replace the P over 2 on the other half. These are identical to each other with the length of L2 and P over 2. And if you remember from previous example, for such combination, delta maximum is 2/3 of PL cubed over EI. If we apply to our category, our beam, it just gives us, you have everything the same, but replace P with P over 2 and L with L over 2, then cubed. And if you do the math, it just gives you PL cubed over 24 EI for this beam. So that's an interesting result. Wow. So if you just consider the a non-prismatic beam of like two simple support with a continuous change in the cross section and a concentrated load of P, we easily calculated the delta maximum, which is PL cubed over 24 EI. And that's also an interesting result. So if you consider a prismatic beam with the same loading, with the same support condition, we already know that the delta maximum for such beam is PL cubed over 48 EI. You can find it in the reference, NCAAS references, and also any other textbook reference that you will find it. So the interesting result is that if you just consider the prismatic beam of a here with the non-prismatic, everything the same, but prismatic versus non-prismatic, you can easily see the delta maximum for prismatic beam is for non-prismatic is as twice of the prismatic beam. So just be careful in designing of non-prismatic. We are more concerned in the double checking the maximum deflection, because the maximum deflection also the beam is much more economically more efficient and uses less material, but the delta maximum is a concern of a calculation and checking. Thank you will solve more problems in beams.